The next section is convergent sequence. The definition of convergent sequence. We say that the sequence of real numbers, we say that the sequence of real numbers which is Sn, denoted as Sn, convergent to some real number L if for every epsilon greater than 0 there exists some natural number or positive integer n such that the absolute value of Sn minus L is less than epsilon for all n greater equal the large n, which is smallest value of n, satisfying the definition of limit of sequence of real numbers. And if the sequence Sn does not have a limit, then we say that the sequence Sn is divergent. That means it does not have any limit L. So example, the constant sequence 1 1 1 1 1 has limit 1. We have seen the example in the last lecture, has limit 1. Therefore, we can say that the sequence 1 1 1 1 1 continuously is convergent to the limit 1. As we have seen, the sequence 1 by n. What are the terms of the sequence? 1, 1 half, 1 by 3, 1 by 4 and so on. We know that it has a limit L equal to 0. So we can say that the sequence is convergent to 0. The real number 0 is the limit of the sequence. Next example, the sequence, or we can have more examples, the sequences n, which is having the terms 1, 2, 3, 4 and so on, and the sequence so it is minus 1 raised to n, minus 1 raised to n. So the terms will be minus 1, 1, minus 1, 1 and so on. This sequence also does not have any limit. This sequence does not have any limit. So both are divergent. Right. So the next theorem it is theorem of uniqueness, and the theorem is, if the sequence of real numbers Sn is convergent to L, convergent to real number L, then the sequence Sn cannot also converge to a limit distinct from L. Limit distinct from L. Or you can simply can have the other statement which have the same meaning. The sequence of real numbers Sn, the sequence of real numbers Sn converges to the unique limit L. That means if a sequence of real numbers is convergent, so it converges to a unique limit. The limit cannot be different. Right? So how to prove? So what can be the idea to prove that the sequence has, if it is a convergent sequence, it has a unique limit. So the idea is, consider, suppose there are two distinct limits and we have to show that, then something will be different, something different will be there. If we consider the sequence has two limits, something wrong will be there. The thing will be not clear by the mathematical concept. So we suppose limit of sequence Sn as n tends to infinity is L, and also we suppose limit of the same sequence is some other real number m also. And what we have considered, suppose the sequence Sn converges to two limits L and m, and they are different or distinct limits. As they are distinct, then their difference, definitely it will be not equal to 0. As difference will be not equal to 0, so absolute value of difference will be definitely a positive real number greater than 0. So now we consider, as L minus m is distinct from 0, so its absolute value is greater than 0. So we take the value of epsilon to be half times this L minus m, and which is definitely positive real number. Since we have assumed limit of Sn as n tends to infinity is L, it means what? By the definition of sequence of limit, it means that for every epsilon greater than 0, there exists or there is a positive integer n1 such that the difference of the sequence and limit L is less than epsilon, and it is true for all n greater equal this natural number or positive integer n1, right? So it means what? The epsilon we have chosen it to be half times L minus m. So I write here Sn minus L should be less than half times absolute value of L minus m. It should be true for all n greater equal n1. So I call it as equation 1. Also, we consider that limit of sequence Sn is something m, right? So by the definition of limit of sequence, it means what? It means for every epsilon greater than 0, there must exist some positive integer n. So I call it as n1 and n2, such that the difference Sn minus L is less than epsilon. What epsilon we have chosen? To be half times absolute value of L minus m, and it should be true for all n greater equal the positive integer n2. So I call it as equation 2. Now we choose n to be maximum of n1 and n2. Then for every epsilon greater than 0, there is positive integer n which is maximum of n1 and n2 such that the difference Sn minus L is less than epsilon. Epsilon is half times absolute value of L minus m, and modulus of Sl minus m, Sn minus m, I have done wrong thing here. It is Sn minus m. Similarly, Sn minus m is less than half times L minus m, and it should be true for all n greater equal n. What n? We have chosen n to be maximum of n1 and n2. So now consider this absolute value of L minus m. So we write this thing by this way: L minus m plus Sn minus Sn. So I can arrange them as Sn minus m plus Sn plus minus m minus Sn minus L in the bracket, right? So I know that by the triangle inequality this thing will be less equal absolute value of Sn minus m plus absolute value of Sn minus L. So by using equation 1 and 2, this thing is less than epsilon, this thing is less than epsilon, and epsilon we have chosen something. So it is strictly less than half times L minus m. This is also strictly less than half times L minus m. So this is by equation 1 and 2. And it is equal to L minus m. So what we get? This implies that absolute value of L minus m is strictly less than L minus m. Is it true? A real number is strictly less than itself is a contradiction. Right? So we cannot have L different from m. Right? So L should be same as m, and our theorem is done. The next theorem. The statement is, if the sequence of real numbers Sn convergent to L, convergent to real number L, then any subsequence of Sn is also converges to the same limit L. So the proof is that let sequence Sn converges to limit L. That means by the definition of limit of sequence, we can write for any epsilon greater than 0, there must exist a positive integer n such that the difference Sn minus L is less than epsilon for all n greater equal the large n. So let me call it as equation 1. So choose a natural number ni greater than n, then there exists some natural number ni greater than n such that every epsilon greater than 0, the difference Sni minus L is less than epsilon, and it is true for all Ni greater than the large n when I is a positive integer. So that means we can say that limit of the sequence Sni is also L. So therefore the subsequence Sni also converges to L. Right. The next thing is corollary. If the sequence of real numbers Sn, if the sequence of real numbers Sn is converges to L, then all the subsequences of Sn also converges to L, also converges to limit L. So proof, it is nothing different from the statement of the above theorem. So by previous theorem, if sequence Sn is convergent to L, convergent to limit L, then L must be unique. And by above theorem, any subsequence of sequence Sn converges to L. So it implies that all subsequences of sequence Sn, all subsequences of sequence Sn are converges to the limit L. So let us see the example. Let sequence Sn is -1 raised to n for a natural number or a positive integer n. So this sequence, so what is Sn? So sequence Sn will have the term -1 + 1 -1 + 1 continuously, right? So this sequence has subsequences -1 -1 -1, which converges to -1 because it is constant sequence, which is subsequence of Sn. And second one is 1, 1, 1. It is also a constant sequence and which converges to limit 1. But what we know, the sequence Sn is divergent. It does not converge to any real number or any limit L, right? But it has a convergent subsequences. So both the subsequences of Sn converges to distinct limits which are -1 and +1, right? So by corollary, given sequence Sn, which is minus 1 raised to n for a positive integer n, is divergent because the subsequences converges to distinct limits, right? And the next theorem is, if sequence Sn converges to L, then the sequence of modulus Sn or absolute value of Sn is converges to modulus of L. So the proof of theorem. So first we prove that for all real numbers a and b, absolute value a minus absolute value b is strictly less than absolute value of a minus b. For this, let consider real number a. Then we have seen this in the real numbers. So I can write this absolute value of a as absolute value of a minus b plus b. So the thing is less equal absolute value of a minus b plus absolute value of b by the triangle inequality, right? So that means I can write it as absolute value of a minus absolute value of b is less equal absolute value of a minus b. It is equation 1. Similarly, do the same thing for b, real number b, and what we get? We will get absolute value of b minus absolute value of a is less equal absolute value of a minus b or b minus a. That is minus of absolute value of a minus absolute value of b is less equal absolute value of a minus b. I call it as equation 2. So by 1 and 2 you can have this thing is less equal modulus a minus b, and by equation 1, by 1 and 2 what we can get? By 2 I can write it as a minus of absolute value of a minus b is less equal absolute value of a minus absolute value of b, and by equation 1 I can write, right? So by the properties of absolute values of real numbers, it implies that absolute value of mod a minus mod b is less equal absolute value of a minus b, and it is what we wish to show here. Now we use this thing. Now, since it is given that limit of Sn is L, so by the definition of limit of sequence, for every given epsilon greater than 0, there must exist a positive integer n such that absolute value of Sn minus L is less than epsilon for all natural number n greater or equal the positive integer n. So then by inequality in 3, by using inequality 3, inequality in 3, absolute value of mod Sn minus mod L should be less equal absolute value of Sn minus L, and by the definition let me call it as equation 4. So, and this thing is less than epsilon. It should be true for all n greater equal n. So, I have written this by equation 4. Right. That means what we have done, the absolute value of mod Sn minus mod L is less than epsilon for all n greater equal n. That is, it implies that limit of absolute value of Sn as n tends to infinity is absolute value of L. Right.